Welcome everybody to the Algebra 2 Chapter 1 review video here, and I apologize if I sniffle or cough a little bit. I do have a little bit of a cold. Um, but what we're going to do is go through the problems that are on your Chapter 1 review guide and hopefully get everything all squared away before we take this Chapter 1 test. So without further ado, let's get started. All right, so the first set of problems, identify the function family to which g belongs. Well, I guess I should say f, all those functions are named f, as well as the parent function for each, then state the domain and range of the graphed function. All right, so let's take a look at what we're working with here in problem number 1. Now, we are dealing with a quadratic family. Okay, and the parent function then would be y equals x squared with no adjustments made on the sides. And then find the domain and range of the graphed function. Well, the domain, all x values that are leading to the graph, and look at that, we got all real numbers. So domain is all real numbers there. And our range, what are the y values that we can see that graph at? Well, every height that's above a height of -1. So my range is all y values that are greater than or equal to a -1. Okay, for the second one, here we are dealing with a linear function, so it's part of the linear family. The parent function there is simply y equals x. Domain, well, eventually that line is going to hit every single x value, so all real numbers for our x. And for the range, it's still going to extend all the way bottom to top, hitting every y value. Also, all real numbers are in that range. And finally here on this slide, problem number 3, this is an absolute value function, a member of that family, parent of which is just simply y equals absolute value of x. And the domain of our graph, well, yet again, all the way from left to right, I'm going to see that graph at every x value, all real numbers. And my range, well, here I see the graph as soon as I'm above the x-axis. So all heights where y is greater than or equal to 0. I want to be sure that we're including that little or equal to underneath. Because that graph does have a point at the bottom. Same with the quadratic there in problem number 1. All right, now this next slide is a little bit more intensive. Graph the function and its parent function. Well, what I'm going to do is I'm going to go through first and graph all the parent functions and describe the transformations, because I think that's going to help me draw the actual function a lot faster. So for the first one, we've got a basic linear function. I'm just going to draw the line y equals x there in red. For number 5 here, I've got the absolute value function that is that V-shaped graph starting at the origin and going up and to the right with a slope of 1 and slope of -1 off to the left. Number 6, I've got a parabola. And we talked about the pattern that parabolas show. Vertex is at the origin. Oh, shoot, I should make that a dashed one. Vertex is at the origin, and then we move away from that origin over 1, up 1 squared, over 2, up 2 squared, over 3, up 3 squared, and so forth, giving us a nice U-shaped graph. Let's look at number 7. Here it's just a constant. Well, parent function there is just y equals 1. So we'll put that in. Number 8, we've got the same absolute value parent. And number 9, we've got the same quadratic parent here. So kind of a Henry Ford assembly line way of doing this. Do all of those parent functions first. And then let's see what the transformations are. That's really going to help us out. So for number 4, this plus 3 is simply telling me up 3 units. So everywhere that I have a point on this graph, if I raise that point 3 units, I will have my new graph. So we'll draw that in, make sure it extends all the way across. If I had a straight edge, I would certainly use it. But here on the smartboard, that is quite an endeavor. Number 5, here we're taking our absolute value parent and we are shifting it down 1 unit. So again, every single point on that absolute value, if I were to drop it down 1, I'm just kind of picking them at random here to get an idea. but after I have a few of those drawn, I get a good idea about where that transformation will be drawn in. Number 6, there's a 1/2 multiplied out front. That is saying 1/2 as tall. And that's how I prefer you answer that question, half as tall. You could say a vertical shrink by a factor of 1/2. That's the textbook's language, though, and I like to think that we have our own more efficient way of communicating that. And all I'm going to do is some places where I knew some heights. So here, if I went away 2, I knew to graph the original, I'd go up 2 squared or 4. But here I only go up half that. And we'll mirror that to the other side. If I go 3, let's see, 4 squared would be 16, so I only want to go up 8 for that one. Half of that would be right there, be right there. So we get our half as tall parabola drawn in. Again, taking the time to plot some points. We grab them out of the calculator, that's fine. But take the time to make an accurate graph. Don't just throw a U on there haphazardly. Now, h of x equals 4, that's taking my y equals 1 parent and adding 3 to it. So I know that that plus 3 that's happening is really an up 3 shift. So I go up 3 units everywhere on that line to get a new horizontal line. We've got 2 things happening here. Problem number 8, we've got a vertical flip, and it's also being shifted down 3 units. So I'm going to take that vertex point and go down 3 units. And then from there, we're going to have our graph take the same slopes off to the sides, but going downward instead of upward because it's been flipped over the x-axis. And then we get to the best one of all. Negative sign out front tells me I've got a vertical flip here. That 3 out front tells me it's 3 times as tall. This plus 3 says I am 3 units to the left. Let me just call that left 3. Okay. So we'll move over to the left 3 units with our vertex. Right there. Instead of going over 1 and up 1 squared, I'm going over 1 and down 1 squared times 3. And after that, we are off our graph. So I want to still be sure that I show a bend. It's not sharp by any means. Still a U-shaped graph. It's just been stretched quite a bit. Of course, we can use our calculator to check all these as we go along, but I think we found an efficient way to do it. We're only 8 minutes into the test here, and we've already gone all the way through 9 questions, so that's pretty good. This next section is one that has stumped students in the past, so I want to be sure that we are taking time to build our function and basically know, are we changing the input of the function or are we changing the output? So here I'm going to take a second to write that out. All right, any change that's horizontal is going to happen outside the function, whereas any change that I'm sorry, I said that completely backwards. Any change that is vertical is going to happen outside. I'm getting ahead of myself here. And any change that is horizontal is going to happen inside with x. So by writing it out that way, we can easily see, do I need to adjust my input x? Or am I just adjusting the function itself on the outside? And here you can see the language that's being used is our formal textbook language. That's totally fine. But just to translate it into our own, let's see. Number 10, we're starting off with absolute value. Reflection in the x-axis, that is a vertical flip. If we are going over the x-axis, we are flipping top to bottom. Translation 4 units to the left. Okay, that means 4 days ahead. If that graph's to the left, that means it's behind us. It's in the past. So just kind of using the language we had from the class. All right, so let's see. For our adjustments, so we're going to write our function g of x. Okay, and it's going to have, first of all, a reflection in the x-axis. Okay, well, that means a vertical flip, so that means I'm taking the negative version of f of x, and that negative is going outside because it was vertical. Okay, then after that, I'm taking it and adjusting it to go 4 units to the left. So that means I need to adjust the input then as well. I need to make it say x plus 4 because we're 4 days ahead of schedule. Now we can finally answer the question, now that we know where our changes are occurring, negative absolute value of x plus 4, when we plug them into the absolute value. All right, for number 11, we got a vertical shrink by a factor of 1/2. That's saying half as tall. Followed by a translation 2 units up. Well, that needs no adjustment for us to understand that. So my function g of x, it's going to be half as tall. That means half of f of x outside. And then a translation 2 units up, that's also an adjustment outside. So my g of x for this problem is going to be 1/2 that absolute value of x, and then plus 2. For problem number 12, here we're starting off with a linear function, and our transformation is 3 units down, followed by a reflection in the y-axis. That's a horizontal flip. Flipping across the y-axis, that's going side to side. So let's deal with the 3 units down first. And you can always break these. I know I didn't do it for 10 and 11, but whenever we see the words followed by, we can break it down this way. We can say, okay, let's handle the first part, this 3 units down, and just call that h of x. That's going to take my function f of x and then subtract 3 afterwards for that vertical adjustment. Okay, so h of x is really going to be x minus 3, because f of x is just really x. Then I can handle the second part, what follows the followed by in our instructions, to find g of x. That's going to take what we'd already done and reflect it in the y-axis. In other words, it's going to input a negative x. Okay, so g of x is really, well, instead of my function h having positive x minus 3, now it will have negative x minus 3. And again, I could have done that in 10 and 11, split it up that way. Usually it's just if you have something happening inside that is happening early, that's when you want to use the h of x. Here again, it's just a matter of keeping things organized more than anything else. All right, we got 2 more of these problems. There's not this many on the test, but like I said, this was a weak point in previous years' classes when they test over this chapter. So I want to give some extra practice for this as we prepare for this year. All right, so 13, we have vertical shrink by a factor of 1/3. Let's handle that first. That is 1/3 as tall. So let's break it down like we did on that last one. H of x is 1/3 of f of x. We're making that adjustment outside. Then we've got 2 units left and 1 unit up. So left means we're 2 days ahead. And then 1 unit up, well, we can do that. So then our g of x is going to apply those transformations to what we already did for function h. So 2 units ahead of schedule, that means I'm taking h of x plus 2. Right? If it's moving to the left, it means it's in the past. We already did it. We're 2 days ahead. And 1 unit up. Final function here, well, h of x is 1/3 f of x. That's really 1/3 of x squared. So I've got 1/3 of x plus 2 squared and then plus 1. All right, number 14, it says a vertical shrink. I think they meant a vertical stretch by a factor of 2. A factor of 2 is going to make it larger. Right? Factor means we multiply in. So let's handle that part first. H of x is going to mean we take our f of x, we make it 2 times as tall, adjust it vertically out front. That's going to mean we have 2 times x squared. Then we have a translation 2 units to the left. Again, that means 2 days ahead of schedule. So for our g of x, we're going to take our h of x and we're going to change the input to x plus 2 to represent that horizontal shift being 2 days ahead of schedule. So to finally answer the question, g of x is 2 times not x, but x plus 2 squared. All right, we're cruising right through this. Given the graph, find the slope of the line and then fill in your answer in the gridded response box. You may have seen this when you practiced for the SAT last year. There are some questions where you don't get an A, B, C, D multiple choice answer. You have to bubble in your answers in a box like this. Nice things to note about these types of questions, they will always be positive, and they always come out to values that will fit in 4 spaces here, unless they tell you to round or something like that. So here, if we find our slope, let's take these 2 points that are given, and we're going to do y2 minus y1 over x2 minus x1. And just grabbing the x and y values out of that table, 30 minus 15 is 15 for our change in height, or change in y, and then 6 minus 1 is 5. That answers 3. So we bubble in a 3, fill in 3 in the box up above, and we are done. Now, you could have entered that 3 in any of the 4 boxes. If you leave the others blank, it will still be marked correct, but I strongly encourage you to put your answer as far to the right as it will fit. So here, this 3 should go in the far right, just to be safe. This next slide is about writing equations of lines. For number 16, excuse me, we're going to write the equation of this line here and interpret its slope. Remember, interpreting just means using units. So if I find my slope first, that's going to be y2 minus y1 over x2 minus x1. That's negative 400 over 4. It's negative 100 for a slope. Then we'll go into point slope form. I really like that 0.1 comma 600. Y minus y1 equals m times x minus x1. We'll distribute on the right, and we'll add over that 600. Negative 100x plus 700 is our answer, and the interpretation of the slope is that sales are falling by 100 million per year. Right? What are our units? Well, 100 million is our y value, per year is our x value. Number 17, here I'm actually going to take a second and pull up a calculator to help with this one. So give me a second while I open that here on this machine. Obviously, sitting there taking the test, you'd be able to open this right away. Oop, I don't want that. I want this. Okay, we'll open a new TI-83 and we'll run it. Okay, so let's open up that and then open that on top. So remember, what we want to do is we want to find a linear regression here. So what I'm going to do is I'm going to go to Stat, and I'm going to Edit Stats. List 1 is going to have all my x values. So I put in 0, 2, 4, 6, 8, and 10. For list 2 come all the y values, 1.24, 1.26, 1.39, 1.47, 1.49, and our last one, 1.57. Okay, then we want to find the equation of that line of best fit. That's again hitting the stat key, go over to calculate, and then option 4, our linear regression. We'll hit enter, and there we have our linear regression. Here I'm just going to grab that screen right there, and then we can go back to our slideshow. So the output of our calculator is saying that our linear regression equation, let's round to 3 decimal places, y equals 0.035x plus 1.23, and it's 230, so we don't need to round that at all. All right, then number 18, also writing the equation of a line. You ride your bike and measure how far you travel. After 10 minutes, you've gone 3.5 miles. After 30 minutes, you've gone 10.5 miles. Write an equation to model your distance. Okay, so I want distance to be an output and time to be an input. So I want my line to be some function where distance depends on time as an input. That means I want some points where my input, my time, is the x value, and the output, miles, is the y value. So 10 minutes, 3.5 miles is that data point. 30 minutes, 10.5 is our second point. And once we have 2 points, we can very easily come up with the equation of this line. You could use linear regression with just 2 points in there. You'd get an exact answer as well. There's a little insider tip for you. But this one is pretty easy to do by hand. y2 minus y1 is 7. x2 minus x1 is 20. There's our slope. Okay, so let's take one of these points that's easier to work with. I think the first one probably. Our equation, y minus 3.5 equals m times x minus 10. Y equals 7 over 20x minus 70 over 20. And then 3.5, that would be 35 over 10, which would be 70 over 20. Oh, so they cancel out. Our y-intercept is 0. And that makes sense, really, now that I think about it. Our y-intercept should be 0 because after 0 time has gone by, I will have traveled 0 distance. Then to finish the question, how far can you ride your bike in 45 minutes? Well, to answer that, I'm going to take y equals 7 over 20 times 45. That would be, I'm going to try and work without a calculator here, 7 over 4 if I divide that by 5 times 9 if I divide that by 5, which gives me 63 over 4 miles. And that makes sense too. That's going to be 60 divided by 4 would be 15 miles. So I know that it's greater than what I did in 30 minutes. So this answer makes sense as well. So there are 2 parts to that question. Okay, our last concept of chapter 1 is solving systems of equations. So here we have the substitution method, the elimination method. We could graph if we want to, although I'm not going to provide graphs for you, so we're going to try and stay away from that approach if at all possible. So as I look at this page, really there's no point where I see the substitution method being faster. That's kind of hopefully what we arrived at just by our own experience going through the problem sets in class. But here, let's take a look at what we can do to solve this. So if I'm trying to eliminate the x's in the first one, I need to adjust that bottom equation by 3. Top equation did not change. My bottom equation becomes negative 3x minus 9y equals negative 18. And if I combine those together, I get 0 equals 0. That system has infinitely many solutions. For number 20, here again, let's try and cancel the y's. They look a little bit easier to cancel from this approach. I don't like this plus a negative 4y. That should just be minus 4y. So negative 3x minus 4y, I'm going to multiply that by 3. So I get 4x plus 12y equals 0 in the top, and then I get negative 9x minus 12y in the bottom equaling negative 30. I find negative 5x equals negative 30, and so x has to equal 6. Okay, so I know there's a solution. Now I just need to substitute that 6 back into one of my equations above and solve for y. So 4 times 6 is 24, plus 12y equals 0. Well, that means 12y equals negative 24, and y has to be negative 2. Okay, and if I were to check my solution, I would simply plug those values for x and y into the equations that I was given. Make sure that they produce the correct solution, a true statement. For number 21, let's eliminate the y's again. I think if I multiply that bottom equation by 3, that I'll be in pretty good shape to eliminate that. And if we combine our x's, I get negative 13x, no y's left, and that equals 39, telling me x is negative 3. So we got a solution. Let's plug it into that bottom equation. Negative 5 times negative 3 is 15 minus y equals 7. Well, if I add 15 to both sides, subtract 15 is negative 8, so y must equal 8. Okay, and for our final two-variable system up here, again, you will not have this many on the test if you're kind of worried about time. You'll not have as many of these either. There are only 2 of these types of problems on your test. So again, extra practice to make sure we're ready. I'm going to cancel out the y's again for number 22. So the bottom equation stays the same. Top equation becomes 15x minus 3y equals negative 33. And when I combine them and get the y's to eliminate, 18x equals negative 54, telling me x has to be a negative 3. Just like the last one. How funny is that? Now if I substitute that negative 3 into the top equation, that has the easier y for me to solve for. I get negative 15 minus y equals negative 11. Add 15 to both sides, negative y equals positive 4, so y must be negative 4. All right, and the final task we have is a couple of 3 unknown systems to solve. And we're pretty lucky on our homework and on our quiz even, we had equations that were all filled in. For this practice, we've got some of those special cases where maybe they're not all x, y, z equations, which is tends to be kind of a nice thing really for us. So for the first one, if I know that x is equal to 4z, why don't I substitute in? This is an excellent candidate for substitution. If I substitute in 4z for x, then I will have used all 3 equations, plus I get 4z plus y plus another z equals 3. Hey, I've got an equation that really just has y's and z's in it. Let's see what happens in that bottom equation. I have negative 4z plus 3y plus 2z equals negative 8. If I combine like terms, that's negative 2z and a positive 3y equal to negative 8. Very quickly, I get to a system of 2 equations with 2 unknowns just by substituting. All right, from there, I think the y's look pretty easy to cancel out here, so I'm going to multiply that top equation by negative 3. I'll have negative 3y minus 15z equals negative 9. Bottom equation will not change. And when I combine those together, I find negative 17z equals negative 17. Z equals 1. So my order triple, I'm thinking that z has to equal 1. Well, just by substituting, I know that x has to equal 4 times z. So x is 4 times 1. It's 4. And then to solve for y, let's plug both of those known values back into our first equation. I've got an x of 4 plus an unknown y plus a z of 1 equaling 3. If I combine like terms and finish solving for y, I find y has to be negative 2. So there's one case where the substitution method really helped us out because it got us to 2 equations, 2 unknowns much faster than if we had to do all that work with our original problems, or original equations, I should say. For number 24, here the change is happening because we already have an equation that's 2 variables, 2 unknowns. So we've got x and y. That means if I can eliminate the z's from these 2 equations, the top and bottom, then I'll have another 2 unknown equation to work with. So I have to eliminate the z in order to work with this middle one that I already know. So let's see, what are the adjustments we have to make? I have to multiply the top one by negative 5 and the bottom one by positive 3. That will set up the z's to eliminate. negative 5x plus 5y minus 15z equals negative 30. And then the bottom equation, when it's rewritten, 6x minus 6y plus 15z equals 27. We know the z's are going to cancel out. I get 1x minus 1y equals negative 3. So then I'm going to take this equation, usually we put a box around them, and combine that with the one up above, and it looks like it's really easy to cancel the x's there. I'm going to take this one times negative 1 and rewrite what I have. So I have the given equation that I'm not changing at all, x minus 2y equals 5, and then the one that came out of our previous work, negative x plus y equals positive 3. That tells me that negative y equals 8, so y has to be negative 8. All right, and now we just work our way back. If y is equal to negative 8, then I'll work my way back. Let's go to this equation. X minus that negative 8 is equal to negative 3. X has to be negative 11. And let's plug both of those into an earlier equation that seems easy to work with. I'm going to choose the top one. So I've got an x that's negative 11 minus a y that's negative 8, so plus 8, plus 3z equaling 6. Well, that's negative 3 plus 3z equals 6. If I add 3 to both sides, 3z equals 9, and divide by 3, z equals 3. So my ordered triple for this system is negative 11, negative 8, positive 3. It's very important that you are staying organized with this, especially when you think that somebody's going to have to read this. I'm going to have to read this and follow along with your work. So make it as easy on the person grading as possible. This was a case where we did use the elimination method, but because we had that middle equation that was given that already had two variables, it made our life a lot easier. There will only be one question like this on the test, so do not feel like you're going to have a ton of writing to do in this section. We're also reducing that. Okay, and finally, a word problem. Systems of equations, very useful in solving conundrums like this. A bakery sells donuts, muffins, and bagels. Bakery makes 3 times as many donuts as bagels. Bakery earns a total of $150 when all 130 baked items in stock are sold. And we have their little menu off to the side as well. Letter A says write a system of equations to model the situation. Well, let's x equal the number of donuts, y equal the number of muffins, and z equal the number of bagels. That's the first important thing. Realize what you're trying to find so you can assign variables to that information. Then we want to look for totals. Okay, so it says they had 130 baked items. That means the number of donuts they had plus the number of muffins plus the number of bagels had to be 130 items total. And then it said they earned a total of $150. Well, that's $1 times the number of donuts they sold, plus $150 for every muffin they sold, plus $120 for every bagel they sold. And then finally, they said they make 3 times as many donuts as bagels. So the number of donuts is 3 times the number of bagels. It's important to realize that the number that is bigger, in this case, the donuts, that is not adjusted. It's really tempting to write that one backwards and say z equals 3x. No, no, no. The number of donuts, x, is 3 times the number of bagels, z. All right, then we've got our system set up. We've secured 2 of the 5 points that this problem will be worth. Now it's time to just bring the thing home. So if we're going to solve this, I know that x is equal to 3z. We can use that little substitution trick that we did in the last problem. So let's go ahead and do that. So I've got 3z plus y plus another z. That is 1y plus 4z equaling 130. And then I'm going to do some scratch work off to the side here. I don't like decimals, so I'm going to work with fractions instead. I've got my 1x, that's 3z. I've got 1.5, that's 3 halves y, plus I've got 1.2, that is 6 fifths z, and that equals 150. If I combine this 3, which is really 15 over 5, with the 6 over 5z I have over here, I can call that 3 halves y plus 21 fifths z equaling 150. I'm sorry, yeah. So let's go ahead and add that in here. 3 halves y plus 21 fifths z equals 150. All right, and we can work with these fractions. Again, a calculator or multiplying both sides by 10, anything like that could get rid of those fractions for us. But man, I don't want to go through all that work and dealing with those huge numbers. So I'm actually going to multiply this top equation by negative 3 halves. I get negative 3 halves y, and then negative 3 halves times 4, that's negative 12 halves z. And then this 130 times 3 would be 390 divided by 2, that's 150, 195? No. Maybe this was a bad approach. I'm starting to realize here that this 12 over 2 is not going to combine equally. But let's see this one through. Okay, so 130 over 2 is 65. 65 times 3 is 195. Yeah, good. So yeah, 1.5 of 130. Okay, and if I combine those together, my y's cancel out, and 21 over 5 minus 12 over 2, well, that's 21 fifths minus, this is really 6, which would be 30 over 5. That's negative 9 over 5. So negative 9 over 5z equals negative 45. Let's multiply both sides by negative 5. So that's 9z equals, well, I'll tell you what, let's divide both sides by negative 9 first. Then I'd have 1/5 z equals 5. Multiply both sides by 5, z is 25. Okay, so we know we got 25 bagels. Then I know that x is 3 times z, so I know that's 75 donuts. We'll go ahead and write it out the fancy way. And I know that x plus y plus z is 130. Well, we've got 100 between these two. That means we're just missing the 30 muffins. And we have it. Okay, so this was a long video. Realize we could have made our life a lot easier just using decimals with a calculator on this last one. And I did kind of, excuse me, I did kind of sit there and think through some of the fraction work just to show you the work by hand and working with fractions and that it is totally possible. We've also covered some ways to check our work here in a calculator. Realize that if you just put an answer down, we are not going to give full credit for that, but it is nice to have technology work for us as well. So that does it for our Chapter 1 review. I hope you have a great time studying for this and that you feel confident coming into the test tomorrow, assuming you watch it the day before. The end.